introduction. I missed that year we spent together in Austin, and it was an honor to have you here. And thank you for inviting me to speak here. I graduated from UT Austin in 2014, and since then I've been working in a company called Aptronic. And we began as very much similar to an academic lab doing research. And over the years, we've worked on a number of different projects, primarily in sort of an advanced robotics space across a few different kind of system paths. So the talk I'd like to give today is focused on one of those paths, which is some exoskeleton work that we've done over the past 3 years or so. And this is the first time that we're showing a lot of this publicly, so I'm excited to get into this with you all. So to start off, just the kind of the framework for the conversation. First of all, I'll talk about the kind of the application space or the application domain that we've been working in. There's a lot of different exoskeletons out there, and they're targeted at many different applications. So we'll kind of scope the conversation up front. And then we'll take a look at some of the state-of-the-art out there. By no means an exhaustive look at other systems, but just to get some of our language established up front. The rest of the presentation is really focused on the 2 systems that we've been working on for the past 3 years. The first of those is called Sagittarius. This is our first pass at an exoskeleton design. The second is a system that we call Apex. This is a system that's more recent, and it's designed given lessons learned from the first system that we worked on. And Apex is also an ongoing effort, so I'll show you sort of current results, but there's more results to come after that. The application domains that we've worked primarily in are shown here. All these domains, emergency response, defense, and kind of futuristic space exploration share similarities in that they require very high performance systems that are not necessarily optimized for cost. They require offloading weight from a user or an operator and offloading that weight to ground, but also being very mission critical and focusing on enhancing performance for kind of a short duration of time. Some of the state-of-the-art systems today out there, and by no means an exhaustive look, but here's a few of them categorized across a few different axes here. On the x-axis is load-bearing versus non-load-bearing. So load-bearing system is something where payload is passed through the exoskeleton structure to ground. Non-load-bearing, any additional mass added to the system is passed to the human's skeletal frame. And then on the y-axis is passive versus active. Passive being typically using springs to store mechanical energy and not requiring any kind of external power source. Active typically uses actuation with an external power requirement. Sort of pros and cons of both of those. Active is typically more versatile. You can do more things if you don't have kind of a simple spring to use. But passive is typically cheaper and less versatile. So that brings us to the first system that I'll talk about today, which is the Sagittarius system. Objective behind the system was a load-bearing device where there can be a torso-mounted payload, and then the system will pass that load to ground in parallel with the human's skeletal frame. As I mentioned before, the application domain really kind of focuses on performance here. So the goal is to make this non-inhibitive, very responsive to the wear and not a slow device, but something that can move quickly. These three things drive at some engineering requirements from kinematics, kinematic alignment with the human, dynamics, mass placement, and volume constraints from a workspace consideration. We also took a look at power efficiency, and this has been kind of an optimization objective from the beginning. And this requirement really drives us towards electric actuation, which is really our kind of our specialty as a company. The next few slides will talk about the control approach behind the system. It uses both feed-forward and feedback control, as I'm sure many of you here on this call are familiar with. And the really kind of the main control interface was targeted at an intuitive force-controlled interface. So the intent was that a pilot could enter the system and then just move around intuitively and have that kind of interaction drive the motion of the system. So early on the project was started by de-risking the control approach. This is an example of just a very simple system that we built using components that we had lying around in our lab. You can see there's an actuator mounted to the table, and that actuator is driving a metal structure with a weight attached to it. The human then puts their arm into this cuff, and there's a cable coming down from that cuff that contains a force sensor, and that force sensor is measuring interaction forces between the human and the exoskeleton or the device. The haptic or feedback control then is trying to minimize this interaction force. And so that's what I mean by this kind of feedback control mentality. You can also layer on top of this a feed-forward controller, of course, by given knowledge of the mass and its location. So this is a block diagram of the control that's used in that video. This is the inner loop here is an actuator force control. So the input port of that is a desired force, and then the objective of that controller is to track desired force as measured by a spring in this case, which is a series elastic actuator. The rest of the control diagram is implementing that cuff force feedback control, or that haptic control. Tau C in this diagram is that haptic measured cuff torque. And that signal passes through a low pass filter and then goes into a compensator that's shown here as CC. That compensator is trying to get the measured cuff torque to track a desired cuff torque. The desired cuff torque in this application is almost always zero. We want to have zero interaction force between the human and the system. But for other applications, you could have non-zero forces such as rehabilitation applications. So that's kind of the control philosophy behind the system. Getting into the design of the system. I'm getting some feedback on someone's microphone. So the system design, obviously this is a full body exoskeleton, but we're going to focus here on the lower body because this is a walking robotics workshop. Each leg has 6 degrees of freedom. 4 of those degrees of freedom are powered. In this case, the abduction and flexion extension at the hip are both powered, and then there's a passive internal external rotation at the hip. The flexion extension knee and flexion extension ankle are both powered, and then there's a passive roll degree of freedom in the ankle. You can see those degrees of freedom here listed on the left side of this picture. On the right side is the sensing strategy used in this device. There's basically 3 interaction ports between the human and the system. 2 of those are located in the feet, and the 3rd is located in the torso. There's a kind of a backpack interface that the human can wear. All 3 of those interfaces have force measurements, so you can measure interaction forces between the human and the exoskeleton at those points. There's also an IMU that's located in the torso, The point of that is to measure the global orientation of the torso relative to the world frame. So these next few videos kind of show some of the system design of this and some of the bring-up process that we used. This is an early prototype of the hip structure and the hip actuation. You can see the ABAD and the flexion extension dots here. These are rotary series elastic actuators. And you can see that the human's able to drive this around pretty easily. These are controlled in a pretty low impedance state. So it's pretty easy for the human to drive around. This is the leg, the structure and the actuation approach for the knee and the ankle degrees of freedom. You can see that the two actuators for the knee and the ankle are pretty similar. The design requirements for this were pretty stringent, so there's a lot of kind of engineering rigor that went into optimizing this design. Things that we considered, obviously maximizing the torque and the speed that the system can produce, and thus the mechanical power, minimizing power consumption, so trying to maximize power efficiency, and that kind of drove us towards linear drive actuators instead of rotary rotational drive actuators. Low profile, so the kind of volume constraints of the system drove us to trying to package this in a small form factor. And then we also used liquid cooling in this design to increase torque density of the motor, a brushless DC motor in this case. And then finally, the ability to measure forces with high degree of sensitivity was also desirable, and so that's led us towards this kind of force feedback series elastic design. This video is just showing that mechanism moving around. So you can see here the motor's driving this linear stage, which then is attached to some linear rails and a linkage that transmits that linear motion into a rotational frame. And then the structure wraps around the human to keep a low profile. This video is showing kind of the progression of our control bring-up strategy. So in that first video that I showed, that was a kind of a test bed actuator. This experiment is using more realistic hardware that would be used in the final, similar to something that would be used in the final system. Here we have a researcher from UT Austin, Bing Han, who was working with us to optimize and to design feedback controllers that were robust. And by that, I mean, when you have a system inside of an exoskeleton and you're trying to control interaction forces, the human's dynamics, their muscles, their skin are inside the feedback loop. And so trying to design robust feedback controllers for the various impedances that the human can have is a challenge. The human can change their impedance by co-contracting and different ways like that. So there's some work that went into this to kind of make the feedback control relatively insensitive to those plant dynamics of the human. Moving forward chronologically, this is a bring up of the kind of the full system, focused here on the feed forward control portion of the system control. So as many of you are probably familiar with, this is just a gravity compensation controller. The hip frame of the system is grounded in this case, but given the the torque controlled actuators, you're able to do pretty good gravity compensation with the device. This is a similar experimental setup, except in this situation, the system's grounded at the feet. Same idea here, gravity compensation with driving the ankles and the knees to balance the upper portion of the system. One of the engineering challenges with exoskeletons, and if you talk to anyone that's been in the space, I think they'll agree that the foot is a very tricky engineering challenge to solve. The approach that we took for this system was to scan the foot profile of various individuals and come up with kind of a generic surface that can be placed inside of a COTS shoe. And the reason for that approach was to try to minimize the relative motion between the human's skeleton and the exoskeleton structure. We also included force sensors in between the human and the structure of the system, but that is one of the kind of the implementation challenges with this approach, is finding quality force sensors for those kind of embedded foot applications. The next system that we designed used a different strategy here, and I can talk about that if we've got time. This is the high-level system control strategy. Like I said before, broken into two different sections. There's a feed-forward portion and a feedback portion. If you look at the controller on the right, the top portion is the feed-forward portion. This is a QP-based gravity compensation controller that is able to take into consideration the contact wrench of the foot with the ground, and it also incentivizes the gravity compensation torques based on the load distribution between the 2 feet in the exoskeleton, using those force sensors in the feet. The lower portion of this controller is the feedback portion. Those are those controllers that we showed videos of previously. And this is where the system is monitoring interaction forces between the human and the exoskeleton and trying to drive those to 0. In this next video, though, this next video is showing only the feed-forward portion of the controller. This is a video showing how this is just demonstrating walking around and moving the system to door, what's going on here. There's central controllers, commanded for all these actions. Takeaways from this are, this profile up there.
Sound is very loud. I cannot hear.
Range of motion. Device. Drawbacks, I think,
Nick, I think you need to mute the video if you can. We can't hear you over it.
Prove that in prior features. Additionally, you see
loud.
So to summarize this effort, the drawbacks of Sagittarius that we wanted to improve, it's kind of heavy at 45 kilograms. This limits the amount of usable payload you can add to the system. While parts of it are pretty low profile, there is some bulk in undesirable places like between the legs. And then the kind of that relative motion between the human and the exoskeleton is undesirable, especially as you start moving more quickly and you have more dynamic types of motions that the human is trying to perform. So that brings us to the next system design, which is Apex, shown here. There's some pretty significant improvements of this system compared to the previous one. We were able to reduce overall mass by half, so 22 kilograms total system mass. Especially, we focused a lot on distal mass, so taking mass away from the feet and moving it up towards the hip and the torso. A big improvement over the prior design is a one-to-one payload. So, the exoskeleton basically can carry itself with a 22 kilogram payload. The speed is improved from 2.5 miles an hour, whatever that is in meters per second, to 2.5 meters per second, which is basically a very fast walk. It's like an uncomfortably fast walk. Low profile design, I'll talk about that more in a moment. And then kind of the last point is focusing a lot on increasing coupling between the system and the human. And there's some mechanical design challenges that come with that, but trying to minimize these kind of uncoupled dynamics between the two systems was a big focus here. And that drives us towards a few kinematic and comfort considerations that I'll talk about in a moment. From a system design perspective, kind of the overall implementation approach was to place structure lateral to the leg and then anterior to the torso. Unlike the prior Sagittarius system, we focus a lot on distal mass and pulling actuation up towards the thigh, towards the torso, and kind of grouping it in that thigh area. There's a lot more cuffing on this system compared to the previous one. So we're cuffing at the feet, the torso, and then also at the thigh and shin links. And because of that increased coupling, that places a more strict requirement on matching the human's kinematics. So that drives us to a bit more complexity in terms of the joints that we use. Not using just pin joints, but some more complex joints. And then we increased degrees of freedom in the leg to add a third degree of freedom in the ankle joint. So this is a roll pitch yaw in the ankle. And then of course, working with humans, you need to have adjustability to match different form factors. So touching on just 3 points of kind of innovation here. One is the ankle. This is a novel ankle design. It's a 3-DOF ankle, so you have those 3 different kind of roll pitch yaw degrees of freedom. And this maintains structural path to ground from the torso. So this was a great improvement in terms of mobility and really just not limiting the human's range of motion in the ankle. Moving up from the ankle to the knee, this is the knee joint. A few things to note here. First, the motor is pulled proximally up into the thigh. So that's advantageous from a distal mass perspective. This is a low friction design that's similar to some other work out there, but there's advantages in terms of efficiency. And then the third thing here is if you look at the knee joint, this is moving not as a pin joint, but as a rolling contact joint, which mimics very closely the human kinematics, which is beneficial from the cuffing that we're using. The last thing here is the spherical hip design. So again, 3 degrees of freedom in the hip, a low profile structural package. And the 3 degrees of freedom are coincident with the human's ball joint in the hip. And in addition, it's really tough to design 3-DOF mechanisms that don't have inconvenient gimbal lock, but this mechanism achieves that as well. So this is the current state of the system. This is back a few months back where we had to pause testing due to coronavirus. But this shows kind of the system as it stands today. Started doing initial testing with a human subject able to walk pretty easily on a treadmill, and then just some burn-in test on a stand here. So we're excited to kind of see what we can do in the future with this system. We think it's a pretty exciting kind of innovative design that has a lot of advantages that we're excited to exploit in the future. With that, I'll stop and take any questions.